there is, somewhere out beyond the small, warm circle of the world we know, a quiet idea that physicists have been turning over in their minds for almost 50 years. It is the idea that the laws which govern everything, the masses of particles, the strengths of forces, the gentle architecture of atoms, may not, in fact, be eternal. They may instead be settled into a kind of comfortable hollow, a resting place that feels permanent because it has lasted longer than mountains and stars and galaxies, but which is not, by the strict accounting of quantum mechanics, the deepest hollow there is. There may be another, lower place. And one day, in some volume of space too distant for any of this to matter, the universe might find it. This is sometimes called false vacuum decay. The phrase sounds dramatic, but the physics that surrounds it is, in its actual texture, very still. It is mostly mathematics. It is mostly the slow, careful drawing of curves on a page, and the working out of probabilities so small that the human mind cannot really hold them. Tonight, we are going to drift through this idea slowly, the way one drifts through a museum at closing time when the lights have already begun to dim. There is no hurry. There is nothing here that needs to be feared. The numbers involved are vast in a way that empties them of urgency. By every reliable measure, this is a story about something that almost certainly will not happen for longer than the universe has yet existed, raised to a power, raised again to a power, and then again. But the idea itself is beautiful. And the science that explores it has, in recent years, brought it down out of the realm of pure speculation and into glass cells of supercooled atoms on tabletops in Trento and Cambridge and Beijing, where small versions of the same mathematics can be watched, gently, under the soft light of laser cooling. We will visit those places before the night is through. For now, settle in. Let the lamp be low. The story begins, as so many stories about the universe do, with the strange and patient question of what the word empty actually means. For most of human history, the answer to that question seemed obvious. Empty meant nothing. Take a jar, pour out the water, pour out the air, pour out the dust, and you would have, at last, an empty jar. The Greeks argued about whether such a thing was possible at all. Some thought a true void was forbidden by nature. Others thought it was simply rare. Either way, the picture was clear enough. Empty space was the absence of stuff. It was what was left when the stuff was taken away. That picture was good enough for ordinary life, and it remained good enough for physics until quite recently. Even Newton, in his slow and majestic equations, treated space as a stage on which things happened. The stage itself was simply there, indifferent and unfilled, waiting for matter to move across it. The vacuum in this old picture was the stage with no actors on it, a silence with no sound to break. But then, in the early 20th century, this picture began to come apart. Not all at once. Slowly, the way old paint flakes away from a wall. The first cracks came from a small detail in quantum mechanics, the new physics that was being assembled to describe atoms. Werner Heisenberg, working in his late 20s, had written down a strange little inequality. It said, in essence, that one could not pin down both the position and the velocity of a small particle at the same time. The more sharply one knew where it was, the more vaguely one knew how it was moving. This was not a statement about the limits of measuring instruments. It was, Heisenberg argued, a statement about the world. There was a kind of irreducible blur built into reality at small scales, a blur that could not be polished away. The implications of that blur for empty space were not appreciated immediately, but they were profound. If you took a small region of space and asked what was in it, the answer could never be exactly nothing. There would always be a faint, uncertain, flickering presence. Fields would tremble. Energies would not quite settle to zero. The vacuum on the smallest scales was not still. It was alive in a quiet, statistical way, like the surface of a pond that is never quite glassy because the air is never quite still. Quantum field theory, which grew up over the next several decades, made this picture more concrete. In quantum field theory, the universe is not built from particles drifting through empty space. It is built from fields, invisible, continuous things that fill every point of space and time, the way water fills a bathtub. There is an electromagnetic field that fills the whole cosmos. There is a field for electrons. There is a field for each kind of quark. There is a field for the Higgs. Particles in this picture are not little marbles. They are ripples in the relevant field, brief disturbances in something that is always there, everywhere, even when nothing seems to be happening. This means that the vacuum, the state of lowest possible energy, the state that physics calls the ground state of the universe, is not empty in the old, intuitive sense. It is a configuration of all these fields at their quietest, their lowest hum. The fields are still present. They cannot leave. There is nowhere for them to go. They are the fabric, and like any quantum thing, they tremble. They cannot be perfectly still. There is always a faint, irreducible motion, called zero-point energy, woven into the loom of space itself. So the vacuum is full. That is the first strange truth one has to absorb to begin thinking about vacuum decay. The vacuum is not the absence of fields. It is the fields settled into their quietest possible state. And what tonight's story is really about is the question of whether that state is actually the quietest state available, or whether there might be another state, somewhere on the energy landscape of the universe, that is quieter still. Let that idea rest there for a moment. The vacuum is full. The vacuum hums. The vacuum has a shape, in the same way that a valley has a shape, and the shape is what we are slowly going to map. There is something gently disorienting about this picture, the first time one truly sits with it. We are accustomed to thinking of the world in terms of objects in space, bodies in motion, things separated by distances, a foreground and a background. The picture from quantum field theory inverts that intuition. The background is the foreground. Space is not a stage with things on it. Space is a layered set of trembling fields, and the things we call particles are no more than the local quivers of those fields, the small standing waves they make when energy is concentrated in one place. A photon, then, is not a tiny bullet of light flying through a void. A photon is a brief, traveling disturbance of the electromagnetic field, the field itself extending unbroken through every cubic centimeter of the cosmos. When the photon arrives at the eye, it is not so much a thing landing as a wave settling. The field receives the energy, and the field passes it on. If this picture is correct, then the question of what counts as empty has to be asked very carefully. One can imagine taking a jar and removing all the air, all the moisture, all the dust, even all the photons one can shield it from. One can cool the jar to within a hair's width of absolute zero. One can wrap it in lead, surround it with superconducting magnets, and isolate it as much as any laboratory has ever isolated anything. And still, inside the jar, the fields will be present. They cannot be evacuated. There is no pump that pumps out the electron field. There is no shielding that keeps the Higgs field out. The fields are part of the geometry of the place. They are part of what space is. Physicists who work with this picture often speak of the vacuum almost the way a musician speaks of a long, sustained quiet between movements. It is not silence in the negative sense, an absence. It is silence in the positive sense, a presence that has settled. The fields are doing what fields naturally do when nothing is asking them to do anything in particular. They are at rest, but the rest itself is a state, with its own properties, its own stability, its own kind of structure. The vacuum has things one can ask about it. It has a temperature in some sense. It has an energy density. It has, perhaps most importantly for our story, a configuration, a particular arrangement of field values that minimizes, locally, the total energy of the system. That last word, locally, is the door through which our entire story enters. A configuration that minimizes energy locally need not be the configuration that minimizes energy globally. There can be more than one valley in the landscape. There can be a deeper hollow somewhere else that the system has not yet found. In ordinary mechanical systems, this is a familiar idea. A ball at rest at the bottom of a small dip is locally stable. But if there is a deeper basin nearby, the ball is, in some larger sense, only resting until it can find its way down. The same idea applies, with all the strangeness of quantum mechanics layered on top of it, to the fields that fill the universe. We do not, of course, know with certainty that there is a deeper hollow, the shape of the energy landscape, beyond the small region we can probe directly, is something we infer from equations rather than measure. But the equations, when extrapolated carefully, do seem to suggest the presence of one, and so the question of vacuum decay, the question of whether our universe, having found a comfortable hollow long ago, might one day, somewhere, slip into a deeper one, is the question of how we ought to feel about that suggested feature of the underlying mathematics. It is, in many ways, a question more about geometry than about physics in the everyday sense. The geometry of an energy curve, the shape of a hidden surface that no observer can ever directly walk upon, but whose contours we can plot, with careful work, on a page. Of all the fields that fill the universe, one in particular is the focus of this story. It is called the Higgs field, and it was named after the British physicist Peter Higgs, who, along with several others working independently in the early 1960s, proposed its existence. The Higgs field has a peculiar property among the fields of nature. Most fields, when left alone in their lowest energy state, settle to a value of 0. The electromagnetic field at the bottom of its potential is just empty. No light, no waves, only the faint quantum trembling we mentioned a moment ago. But the Higgs field, when it settles, does not settle to 0. It settles to a particular non-zero value. It is, in a sense, switched on, and it has been switched on throughout all of space for nearly the entire history of the universe. This is not a small detail. It is the reason there is a universe of the kind we recognize. The non-zero value of the Higgs field is what gives most of the elementary particles their masses. Electrons, quarks, the W and Z bosons that carry the weak nuclear force, all of them acquire mass through their interaction with the Higgs field. Photons, which do not interact with the Higgs in this way, remain massless. So the structure of matter as we know it, the difference between the heavy and the light, the way atoms hold together, the way light streams through the cosmos at the speed it does, all of this can be traced back to the Higgs field having found, long ago, a particular comfortable value, and stayed there when physicists at the Large Hadron Collider in Geneva announced, in the summer of 2012, that they had found the Higgs boson. What they had really found was a small, brief disturbance in this background field, a ripple that the field made when it was struck hard enough by colliding protons. The boson is the field's local quiver, a sign that the field is real, a signature that confirmed an idea that had been waiting 48 years for proof. The boson's mass turned out to be roughly 125 times the mass of a proton. A specific number, measured carefully, with error bars that have grown smaller every year since. The discovery was the result of an enormous, decades-long effort. The Large Hadron Collider itself is a machine of almost geological scale. It is a ring of superconducting magnets and beam pipes buried roughly 100 meters beneath the farms and forests on the border between France and Switzerland, 27 kilometers around. Protons are accelerated within this ring to within a small fraction of a percent of the speed of light, and then guided into head-on collisions inside enormous detector caverns, where the resulting debris of particles is recorded by instruments roughly the size of cathedrals. ATLAS and CMS, the two largest of these detectors, are layered onion-like structures, each made of millions of individual sensors, each capable of recording millions of collisions per second. From the patterns in the debris, physicists slowly, statistically, build up a picture of what the protons made when they collided. And in those patterns, in 2012, two independent teams found the same small statistical bump in their data, near a mass of 125 gigaelectronvolts, in just the places the equations had predicted a Higgs-like signal would appear. When Peter Higgs, by then well into his 80s, was invited to attend the announcement at CERN, he is reported to have wept quietly when the result was revealed. He had proposed the field, with no certainty that it was anything more than a useful theoretical idea, in the early 1960s. He had not expected, in his lifetime, to see it confirmed. Other physicists working at the same time, including Francois Englert and the late Robert Brout in Belgium, had independently developed essentially the same mechanism. And in 2013, Higgs and Englert shared the Nobel Prize in Physics for their work. Brout, having died in 2011, did not live to see the announcement. The shared origins of the idea are sometimes acknowledged in the longer name, Brout-Englert-Higgs mechanism, though the shorter name has settled into the language. What none of them could have known in the early 60s was that the precise mass of the Higgs boson would carry within it information about the stability of the universe. That information had to wait until the boson was found. Once it was found, and once the top quark mass had been measured precisely enough, the top quark having been discovered in 1995 at Fermilab in Illinois, physicists could finally assemble the full picture of the Higgs energy curve at high field values. They could draw the long, extrapolated landscape. They could ask the question, do we live in the lowest valley or only in a high one? That number, 125, is more important than it might appear, because it tells physicists something about the shape of the Higgs field's energy landscape. The Higgs field, like any field, has a kind of map. At every possible value the field could take, the universe would have a particular energy. If you draw this on a graph, with the value of the field on the horizontal axis and the energy on the vertical axis, you get a curve. The curve has hills and valleys. The field, like a marble, will roll downhill, looking for the lowest place it can find. And the lowest place it has found, so far, is the value where it currently sits. The value that gives electrons their mass. The value we have always known. The shape of that curve, near the bottom of our valley, is something we can probe in the laboratory. The mass of the Higgs boson is, in technical terms, related to the curvature of the potential at its minimum, to how steeply the energy rises as you nudge the field a little to either side of its resting value. So when ATLAS and CMS measured the mass of the boson, they were really measuring the steepness of the walls of our valley. They were beginning to draw the curve. The further out you want to extrapolate that curve, the more you have to rely on the equations of the theory rather than on direct measurement, and the more carefully you have to track the small uncertainties. The question is whether this is really the lowest place. Whether the curve, if you keep drawing it out to higher and higher values of the Higgs field, eventually turns over and dives toward a deeper valley. If it does, then our familiar valley is not the lowest one. It is just a valley. A pleasant, comfortable, long-lasting valley, but a valley with another valley below it, separated by a hill. To draw the curve out far enough to see whether this is the case, physicists have to do something extraordinary. They have to use the equations of the Standard Model, the theory that describes the Higgs and all the other particles, to extrapolate the shape of the energy landscape to field values that are utterly beyond what any laboratory can ever produce. The Large Hadron Collider's collisions probe energies of around 14 trillion electron volts. The interesting region of the Higgs landscape, where the curve might turn over, lies around 10 to the 11th power giga-electron volts. That is roughly 10,000 trillion times higher than anything we can directly create. We are, in a real sense, asking the equations to tell us about a place we cannot visit. The technique by which this is done is called the renormalization group. It is a method developed in the 1970s and refined in the decades since, for tracking how the parameters of a quantum field theory change with the energy scale at which one looks at them. At low energies, the energies of everyday physics, of atoms and molecules, and the inside of an atomic nucleus, the parameters of the Standard Model take particular values. At higher energies, those same parameters take different values, and the way they change is determined precisely by the structure of the theory itself. By solving the renormalization group equations, one can extrapolate the Higgs self-coupling, a quantity that controls the steepness of the energy curve, out to enormously high field values, and see what shape the curve takes there. What the equations seem to say, with caveats, with uncertainties, with margin for error, is this. Given the masses we have measured for the Higgs boson and for the top quark, the heaviest of the elementary particles, the shape of the Higgs energy curve does turn over. The curve does seem to dive. Somewhere far above the energies we can probe, our valley gives way to a deeper valley. Our universe, if these calculations are taken at face value, is not the deepest possible state. It is sitting in a high valley, separated from a deeper one by a long, broad hill. Physicists call this state metastable. Stable, in the sense that the marble is not going to roll spontaneously over the hill on any short timescale, but meta beyond, secondary, in the sense that the deeper valley exists, and the marble could, in principle, find its way there. The current best calculations within the Standard Model suggest that this is the situation we are in. Our vacuum is metastable. It has lasted 13.8 billion years, the entire age of the universe, without trouble. By every measurement we can perform, it appears safe. But the calculations also say that, somewhere in that high mathematical territory beyond direct experiment, the floor begins to slope towards something deeper. It must be said that this conclusion is sensitive. It depends precisely on the masses of the Higgs boson and the top quark, and to a lesser extent on the strong coupling constant, which describes how tightly quarks bind to one another. Move the top quark mass up a little, and our vacuum becomes stable. The curve never turns over. Move it down a little, and the vacuum becomes more deeply unstable. The deeper valley opens up sooner. The current measured values place us, intriguingly, very close to the boundary line that separates stability from metastability. Not deep inside one region or the other, but right along the edge. Some physicists find this fact remarkable. Others suspect it points to physics we have not yet discovered, lurking at higher energies, that would smooth the curve out and remove the second valley altogether. The mystery, for now, remains. There is also the matter of what lies beyond the standard model. The standard model is not, almost certainly, the whole story. There are unanswered questions it cannot address: the nature of dark matter, the smallness of neutrino masses, and the puzzle of why the universe contains so much more matter than antimatter. New particles, new fields, and new interactions discovered in the future could reshape the energy landscape entirely. The second valley might be drawn back upward and closed off, or it might be drawn deeper. We do not know. We are, in this story, working with the best map we currently have, while knowing that the map may be imperfect. So that is the situation as it stands. There is a field, called the Higgs, that fills all of space at a particular non-zero value. That value gives our universe its masses, its forces, its furniture, and that value may not, after all, be the lowest the field could take. There may be a place lower still, hidden behind a hill of energy. The marble, if you imagine the field as a marble, sits in our valley. It has been there as long as anything has been anywhere. But the question of whether the deeper valley exists, and what would happen if the marble ever found its way there, is the question that physicists have been quietly turning over in their minds since the late 1970s. To picture the Higgs energy landscape more clearly, it helps to imagine it as a long, gentle terrain. To the left, at small values of the field, the curve rises like the wall of a bowl. As you move to the right, into our familiar valley, the curve drops down to a minimum. That minimum is where we are. That is the everyday world. The Higgs field sits there, at a value of about 246 in the units physicists use, and stays there, and gives mass to electrons and quarks, and to the carriers of the weak force. Now imagine continuing to walk to the right, to higher and higher values of the field. For a long stretch, the curve climbs gently. The field would have to acquire a lot of energy to reach those values. It does not naturally want to be there. The wall of the valley keeps rising. This is the hill that protects us. As long as the marble of the Higgs field does not climb that hill, our world is stable. But somewhere, far to the right, at field values around 10,000 trillion times higher than where we sit, the curve, in the calculations, begins to turn. It pauses, it tilts, and then it slopes downward. From that point on in the mathematical landscape, the curve slides down without coming back up. There is no second hill on the other side. The energy keeps falling. The deeper valley does not have a floor in any well-behaved sense. It just keeps going deeper and deeper into territory where the equations themselves begin to lose their reliability. This is what the standard model, extrapolated to those very high field values, seems to predict. A precipice beyond a long climb. The hill between our valley and that precipice is enormous. It is so high and so wide that the marble of the Higgs field has essentially no chance, on any reasonable timescale, of climbing over it. By any classical reasoning, our vacuum is safe. We are sitting in a deep, comfortable hollow, with a tall, broad mountain between us and any trouble. But quantum mechanics does not obey classical reasoning. Quantum mechanics permits something strange, something that has no analog in everyday physics. It permits a particle or a field to pass through a barrier without going over the top. This is called tunneling. In tunneling, a quantum object simply appears, with some small probability, on the far side of a barrier it does not have the energy to climb. It is one of the genuine mysteries of the quantum world, and it has been observed, repeatedly and reliably in experiments. Radioactive nuclei tunnel out of their parent atoms. Electrons tunnel through insulators in scanning tunneling microscopes. The sun shines in part because protons tunnel through electrical barriers in its core to fuse together. Tunneling is a real, measured, daily phenomenon. The question then is whether the Higgs field can tunnel. Whether, somewhere in the vast volume of the universe, the field can slip from our valley, through the hill, and emerge on the far side in the deeper valley. The probability of this, per unit time, per unit volume, is what determines the lifetime of our vacuum. If the probability is high enough that we would expect a tunneling event somewhere in the observable universe over a span of, say, 1 billion years, then the universe is in trouble. If the probability is so low that we would not expect a tunneling event anywhere in a volume the size of the observable universe over trillions upon trillions of years, then the universe is, for any practical purpose, safe. The first careful calculation of this probability was done by an American physicist named Sidney Coleman and published in 2 papers in the journal Physical Review D in 1977. The first paper was titled, with Coleman's typical understated humor, Fate of the False Vacuum, Semi-Classical Theory. The second paper, written with his colleague Curtis Callan, addressed corrections to the first. Together, these 2 papers laid the foundation for everything that has been written about vacuum decay since. They are, to this day, among the most cited papers in theoretical physics. They are also, for the patient reader, beautiful documents, careful, dense, and quietly profound. Coleman himself was a remarkable figure in 20th century theoretical physics. He spent most of his career at Harvard, where his lectures on quantum field theory became famous. Recordings of them have circulated for decades among graduate students, and the textbooks that grew out of them are still read today. He was known for a precise, dry wit, for an unusual gift of expressing technical material clearly without diluting it, and for a habit of sleeping through the day and working through the night. The papers on the false vacuum were written during his most active period, in the mid-1970s, when he was thinking carefully about the implications of quantum tunneling at the level of fields rather than particles. He worked closely with Frank DeLucia, in particular on the question of how gravity affected the decay rate. And the joint paper they published in 1980, called Gravitational Effects on and of Vacuum Decay, remains another foundational document of the field. Coleman's contribution was to show how to calculate, in the framework of quantum field theory, the rate at which a field could tunnel from one valley to another. He showed that the way to think about it was not in terms of the entire field shifting at once, which would be impossibly improbable, but in terms of small bubbles of the new vacuum forming, here and there, by tunneling. A bubble would be a tiny region of space, a few subatomic distances across, in which the Higgs field had jumped to its new, lower value. Inside the bubble, the new physics would prevail. Outside, the old physics would continue as before. The mathematics of how this happens involves a clever trick called the instanton. An instanton, in the language of quantum field theory, is a particular kind of solution to the field equations in which space and time are treated, briefly, as if they had 4 spatial dimensions and no time at all. It is a piece of mathematical sleight of hand, but a rigorous one, and it allows physicists to calculate quantum tunneling probabilities by finding the shape of a 4-dimensional bubble that minimizes a quantity called the Euclidean action. The smaller the action of this bubble, the more likely the tunneling event. The larger the action, the more strongly the event is suppressed. Coleman's papers showed how to compute this action, in the limit where the energy difference between the two valleys is small, and how to interpret the result in terms of the probability of bubble nucleation per unit volume per unit time. The technique has been refined and extended by many others since, but its essential structure has remained. The fate of any such bubble would depend on its size. Coleman showed that there was a critical radius. A bubble smaller than that radius would shrink and disappear, the way a small, unstable soap bubble pops back into nothing. A bubble larger than the critical radius would grow. The energy difference between the deep valley inside and the higher valley outside would push the bubble's wall outward. The bubble would expand. And due to the equations of relativistic field theory, it would expand at very nearly the speed of light. Its wall, a thin shell of frenetic field motion separating the old vacuum from the new, would race outward through space, converting everything in its path. The reason the bubble expands so quickly is that, once it is past the critical size, there is no longer any energetic obstacle to its growth. Inside the bubble, the field has fallen into the deeper valley, releasing energy. That released energy goes into accelerating the wall outward. The wall accelerates and approaches the speed of light asymptotically, closer and closer, but never quite reaching it, in the same way that a particle accelerated by an unending force in special relativity approaches, but never quite reaches the universal speed limit. From the perspective of any observer outside the bubble, the wall might as well be moving at the speed of light. There is no meaningful sense in which it is slower. By the time the wall has been growing for a few microseconds, it is moving so close to the speed of light that the difference is irrelevant for any observation that could ever be made. This is the image at the heart of the story. A bubble nucleating somewhere, a single point in the vast cosmos, and then growing, like a soap bubble blown by a child, except that its wall moves outward at the limit of all possible motion. Anything ahead of the wall is still in our familiar universe, our valley, our laws. Anything behind the wall is in the new universe, the deeper valley, with whatever physics lives there. The wall itself is the boundary between two different sets of natural laws. It is worth pausing to notice how strange this is and how quiet. There would be no warning. The wall travels at the speed of light. Light is the fastest signal that anything can send. Nothing, no flash, no shudder, no gravitational disturbance, could outrun the bubble's edge to give an observer ahead of it any indication of what was coming. By the time any signal arrived, the bubble would have already arrived. The transition would not be a slow approach, like a storm front rolling in. It would be a sudden replacement, like a switch being thrown. One instant, your atoms would be sitting in the universe you have always known. Next, they would be inside the bubble, where the field has a different value and the rules are different. There would be no perception of it. Perception itself depends on chemical reactions, on electrons moving in particular ways, on protons holding nuclei together with particular forces. All of those processes depend on the value of the Higgs field. Change the field, and you change the very mechanisms by which a brain forms a thought. The thought, mid-formation, would simply have no foundation any longer. It would not be completed. The lights would not so much go out as never have been on at all in the new physics. There is something strange and almost peaceful in that. No suffering, no realization, only an arrival of new conditions, instantaneous and quiet, in which the old conditions cannot persist. Coleman noted, in the closing paragraph of his 1977 paper, that the discovery of vacuum decay would have, as he put it, the ultimate cosmic consequence. He went on, with the dry restraint that characterized his writing, to say that one should not be unduly disturbed by this possibility, given the calculated rates. The numbers, as we will see, are reassuring, but the picture itself, the image of bubbles of altered physics blooming in the dark and expanding silently outward, has lodged itself permanently in the imagination of anyone who has thought carefully about it. What would the inside of such a bubble actually be like? This is a question that physicists have tried to answer in various ways, depending on which set of assumptions they make. The honest answer is that no one knows for certain, because the inside of the bubble would be governed by a different set of physical laws, and we cannot directly explore those laws from where we are. But the calculations within the standard model, extrapolated, give a few hints. In the deeper valley of the Higgs field, the field would have a much larger value. Much larger. Many orders of magnitude larger than the value we live with. Since the masses of particles depend on the Higgs field, particles in the new vacuum would have very different masses. Electrons in the new vacuum would not weigh what electrons weigh here. Quarks, similarly, would have different masses. The proton, which is built from quarks bound by the strong force, would either be bound differently or not bound at all. Atoms, which depend on a particular delicate balance between electrons and nuclei, would not form in the way they form now. In some calculations, the field value in the deeper valley is so large that the energy density of empty space inside the bubble becomes enormous and negative. A region with a large negative energy density does something dramatic in general relativity. It collapses. It pulls itself together, gravitationally, into a singularity. So one possibility is that the inside of a bubble of true vacuum would not be a tranquil new world with different physics. It would be a region collapsing, almost instantly, into a kind of crunch. A singular point where the equations of general relativity break down, surrounded by a wall expanding outward at the speed of light. The interior would be, in some technical sense, an anti-de Sitter space, and an anti-de Sitter space cannot support stable structures of the kind we recognize. It cannot support stars. It cannot support galaxies. It cannot support, almost certainly, anything that resembles life. This is a sober picture, but it is not, in the way the topic is sometimes imagined, a violent one. There would be no fireworks. There would be no explosion. From the outside, even if you could somehow see the bubble, which you could not, because no signal escapes its leading edge, it would simply look like a region of darkness, a sphere of nothing where there used to be stars. The stars would not be destroyed in any dramatic sense. They would simply no longer be possible. The atoms that made them would no longer be atoms. The light they emitted would no longer be light in the same form. The conditions for being a star would have been silently replaced. To linger for a moment on what the change in the Higgs field value would mean, in concrete terms, even though the picture is, by the nature of the topic, somewhat speculative. The mass of the electron in our universe is about 500,000 electron volts. That mass is what determines the size of atoms. It sets the typical separation between the nucleus and the electron cloud. And through that, it sets the size of molecules, the strengths of chemical bonds, the wavelengths of visible light absorbed and emitted by ordinary matter. Change the electron's mass, and you change the size of every atom. Make the electron heavier, and atoms shrink, becoming much more compact, and chemistry as we know it does not occur. Make the electron lighter, and atoms grow, becoming sprawling and weakly held. And again, chemistry does not occur in any familiar way. The same applies to the masses of the up and down quarks, which determine the masses of the protons and neutrons, which determine the size and binding energies of nuclei. A new vacuum, with a different Higgs field value, would shift all of these masses simultaneously in ways that would not preserve the delicate balances that allow ordinary matter to exist. There is a thought experiment, sometimes invoked in popular accounts, of an observer being engulfed by such a bubble. The thought experiment cannot be taken literally. There is no observer in any meaningful sense before, during, or after, but the picture is sometimes used as a way of conveying the suddenness of the transition. The body is made of atoms. Atoms are made of electrons orbiting nuclei. Nuclei are made of protons and neutrons, which are themselves made of quarks. All of these particles get their masses from the Higgs field, so the moment the wall passes through, every electron, every quark, every proton, every neutron would find itself with a different mass. The atomic structure that depended on those masses would be undone, not slowly, but all at once. The electromagnetic forces that hold molecules together would still operate, but they would be operating on entities that no longer fit the patterns required for chemistry. There would be no time for any of this to be felt or registered. The arrival of the wall is the arrival of the new conditions, and the new conditions do not include the kinds of processes that produce sensation or thought. In some scenarios, the new vacuum would not even support stable matter at all. Quarks, in the new conditions, might not bind into protons. Protons, if they did exist, might be unstable on extremely short timescales, decaying into showers of lighter particles, the kind of organized, bound, persistent structures that constitute matter. As we know, it requires very specific values for the masses and couplings of fundamental particles. And there is no general reason to expect those specific values to obtain in a different vacuum. The interior of a bubble of true vacuum, in many calculations, is therefore a place where the very category of matter, bound, structured, persistent stuff, does not really apply. Whatever the field is doing inside, it is doing so in a configuration that has no atoms, no molecules, no astronomy in any sense we would recognize. The bubble's wall, the thin shell where the field is in transition, carries an enormous amount of energy. That energy comes from the difference between the high valley and the deep valley. As the bubble grows, the wall sweeps up that energy and converts it into a kind of radiation, particles, and excitations of various kinds, depending on the precise shape of the potential. Some of this would be visible if you could observe the wall from a safe distance, which, again, you could not. But mathematically, the wall is a region of intense activity. It is the place where physics is being rewritten. Now and then, in the literature, one comes across speculations about what might happen if two bubbles, nucleating in different places, eventually grew large enough to collide. This is sometimes discussed in the context of the early universe, and in models of eternal inflation, where bubble collisions might leave faint imprints on the cosmic microwave background that we could, in principle, look for. We have not seen any such imprints. The cosmic microwave background, as it has been mapped to ever finer detail by the COBE, WMAP, and Planck satellites, looks remarkably smooth. Whatever bubbles may have formed in the very early universe, none of them seem to have collided with our own corner of space in a way that left a trace. There is something gentle in the realization that, if vacuum decay is indeed the eventual fate of the universe, it will be a quiet fate, not loud, not announced, not narrated by any observer. The universe will not, in any meaningful sense, end with a bang. It will, if it ends this way at all, end without a sound. A boundary will pass through unseen, and then there will be no observer left to know that anything has changed. From the outside, in regions still untouched, the change will look like nothing at all, until the wall finally arrives in its own moment, at its own pace. Never faster, never slower, always the same speed as light. It is worth lingering on this thought a little longer. Most images of cosmic catastrophe involve sudden, perceptible violence. The collision of galaxies, the detonation of a supernova, the roar of a black hole consuming a star. Vacuum decay would not be like any of these things. It would be a phase transition, an alteration of the underlying conditions, a quiet substitution of one set of laws for another. The bubble's wall would not be hot in any familiar sense, although it would carry a great deal of energy. It would be more like the silent boundary between two phases of matter, between water and ice, between liquid and vapor, except on a cosmic scale, and with the difference being not in the substance, but in the very architecture of physical law. There is, in nature, a familiar analog that helps make this picture more intuitive, even if only by gentle metaphor. Consider supercooled water that has been carefully cooled below its normal freezing point, to perhaps -10 or even -20 degrees Celsius, while remaining, for the moment, in liquid form. This is metastable water. It wants to be ice. The crystalline form is energetically lower. Ice has less free energy than supercooled liquid water at those temperatures. But there is an energy barrier to becoming ice. The first crystal has to form. That first crystal is the seed, the nucleation point. Until the first crystal forms, the water remains liquid, in defiance of what one might naively expect. The barrier protects it. Now disturb the water, strike the bottle, drop in a single grain of dust, lower a thermometer with a small imperfection on its surface. A crystal forms. From that crystal, ice grows outward, sometimes shockingly fast, racing through the liquid in a cascade of crystallization that converts the entire bottle to ice in a matter of seconds. There are videos of this online. Very pleasant to watch. Slow streams of ice radiating outward from a point of disturbance through a liquid that, until the disturbance, had appeared perfectly stable. False vacuum decay, in its mathematical structure, is the cosmological cousin of this familiar process. The supercooled water is the false vacuum. The ice is the true vacuum. The disturbance, the dust grain, the imperfection, corresponds to the rare quantum fluctuation that nucleates the first bubble. The crystallization front sweeping through the liquid corresponds to the bubble wall sweeping through space. The analogy is not exact. The cosmological version proceeds at the speed of light, while the freezing of supercooled water is much slower, governed by ordinary thermodynamics rather than relativistic field theory, but the underlying mathematical pattern is the same. A metastable state, with a barrier, awaits the formation of a critical seed, after which the lower energy phase grows outward and replaces the higher energy one. Coleman, in his original paper, drew this analogy explicitly, and it remains one of the most useful pictures for thinking about what false vacuum decay actually is. When physicists first began to write about this scenario in the late 1970s and early 1980s, there was a brief period when the public imagination seized on it, and a number of essays appeared with titles suggesting that the universe might be only one tunneling event away from oblivion. This imagery is not entirely wrong, but it tends to obscure the most important fact about vacuum decay, which is that the calculated rates are extraordinarily, almost incomprehensibly small. The story is not really about catastrophe. The story is about the deep stability of physical law over timescales that dwarf the lifetimes of stars, of galaxies, of the universe as we know it. So let us turn to the numbers. The numbers are themselves a kind of meditation. How long is the lifetime of the false vacuum if our vacuum really is false? Coleman's original framework gives a way to calculate this, in principle, from the shape of the Higgs potential. The result depends on a quantity called the Euclidean action, often written as a capital B, that measures the cost, in a particular technical sense, of nucleating a bubble, the probability per unit volume, per unit time of a bubble appearing, is then given by a formula that includes a factor of e to the negative b over h bar. When b is large compared to h bar, this exponential is very, very small. Very, very small. Smaller than any number that has any practical meaning. Modern calculations, performed with great care over the last decade, give a specific estimate within the standard model, given the measured masses of the Higgs and top quark, the expected time for a bubble of true vacuum to form within a region of space the size of a cubic gigaparsec. A volume containing many millions of galaxies is on the order of 10 to the 794th power years. A more recent calculation, published by a group of physicists from Slovenia in 2024, refined this estimate slightly, suggesting the figure might be closer to 10 to the 790th power years. As one of the writers covering this revision in Quantum magazine pointed out, a change by a factor of 10,000 sounds enormous, but compared with the central number itself, it is utterly negligible. The two estimates are, for any practical purpose, the same. Try, for a moment, to feel the size of these numbers. The age of the universe is roughly 10 to the 10th power years. That is, 10 billion years, give or take. 10 to the 790th is the age of the universe multiplied by itself nearly 80 times. 10 to the 794th, similarly. These are not numbers that describe anything in human experience. They are numbers that describe a kind of patience so vast that it ceases to be patience and becomes something more like permanence. If you could somehow exist for 10 times the current age of the universe, you would still be only 10 billion billionth of the way toward the expected vacuum decay event in your local volume. It helps sometimes to picture these numbers in concrete imagery, even though no concrete image can ever do them justice. Imagine a single grain of sand. Imagine that the entire age of the universe to date is represented by that one grain of sand. Now imagine, for 10 to the 790th power years to pass, you would need to gather that many grains of sand, one for each universe age that elapses. The number of grains of sand on Earth, all of them, all of the beaches and deserts combined, has been estimated at perhaps 10 to the 18th power. That is, a 1 followed by 18 zeros. To fill out the timescale we are talking about, you would need to multiply the entire surface of Earth by itself, and then by itself again, and again, and again, several dozen times over. The numbers are not just large. They are large in a way that the everyday vocabulary of large numbers, the words billion, trillion, and quintillion, does not begin to capture. There is another way to put this. The sun will burn for another roughly 5 billion years before it swells into a red giant and consumes the inner planets. In about 100 billion years, the last galaxies receding from us will pass beyond the edge of our observable horizon, and our local group of galaxies will appear, to whatever observers remain, to be alone in a darkening sky. In 100 trillion years, the last stars will go out, having exhausted their fuel. In a Google years, 10 to the 100th power, the supermassive black holes at the centers of dead galaxies will themselves have evaporated through Hawking radiation, leaving the universe a thin, cold soup of photons and the occasional stray particle. All of these epochs, including the slow death of the last black holes, will have come and gone long before. By the central estimate, a single bubble of true vacuum is expected to nucleate in our cosmological volume. Even after the last black holes have evaporated, the universe will continue. It will be cold, dark, vastly empty, with the average temperature approaching absolute zero, and the density of matter so low that any region one could pick out at random would, on average, contain no particles at all. That long, cold, quiet era is sometimes called the dark era of the universe, and it is expected to last, by some accounting, until the observable universe consists of a single particle drifting through an unimaginably vast and otherwise empty volume. And even that era, by the central calculations, will pass before vacuum decay becomes statistically expected. The numbers are deeper than the universe's longest known scenarios. So when one reads, in a sensational article, that vacuum decay could end the universe at any moment, the statement is technically true, and yet practically very strange. At any moment, one could tunnel through the floor of one's bedroom due to the same quantum tunneling rules. The probability is just absurdly low. Very, very low. The probability for vacuum decay is, by current calculations, far lower than that. The phrase "at any moment" really means at any moment in a stretch of time, longer than every cosmological epoch combined, raised to a power. It is worth dwelling on this point, because the sensational framing of vacuum decay sometimes obscures the real character of the science. The real science is not a story of imminent catastrophe. It is a story about the long, slow stability of the laws of physics, about the depth of the valley we sit in, and about the careful mathematical work needed to determine just how deep that valley is. The numbers, when examined, are themselves the reassurance. There is no need to fear what is being calculated. The calculations are precisely what tell us that, in any sensible accounting of cosmic time, fear is the wrong response. Curiosity, perhaps. Wonder, certainly. All at the depth of stability that 13.8 billion years can represent, but not fear. Fear is for things that are about to happen or that are happening now. The vacuum, by every measurement we can perform, is not about to do anything. There is also a strong observational argument that the true rate cannot be much higher than these calculations suggest. The argument goes like this. The universe is roughly 13.8 billion years old. In all that time, in all the volume that we can see, and the volume we can see is enormous, containing somewhere on the order of 2 trillion galaxies, no bubble has yet arrived. We have not been swept by a wall of true vacuum. The cosmic microwave background, which gives us a snapshot of the universe as it was 380,000 years after the Big Bang, looks calm and smooth across the entire sky. Whatever was happening in the very early universe, our region of it was not destroyed by any phase transition that left visible scars. This places a real, observational lower limit on the vacuum's lifetime. Whatever the precise rate, it cannot have been so high that bubbles should already have been observed. And given the size of the observable universe, this constraint, combined with the theoretical calculations, is consistent with the picture of an extraordinarily long-lived vacuum. The universe is, by all measurable accounts, sitting in a hollow so deep and so stable that the question of when it might next find a deeper hollow is essentially academic on any timescale we can imagine. There is also the question of cosmic rays, which provides another quiet line of reassurance. Cosmic rays are particles, mostly protons, that travel through space at extraordinary energies. Some of them, the so-called ultra-high-energy cosmic rays, carry energies far in excess of anything humans have ever produced in particle accelerators. They have been doing so for billions of years, striking the atmospheres of every planet, every star, every cloud of gas in every galaxy, in every part of the observable universe. When physicists were considering, in the years before the Large Hadron Collider switched on, whether the LHC's high-energy collisions might somehow destabilize the vacuum, the answer that emerged from the LHC Safety Assessment Group was simple. Cosmic rays already produce far more energetic collisions, far more often, all over the universe. By their estimate, nature has been performing the equivalent of around 10 to the 31st power LHC experiments over the lifetime of the universe, and continues to perform something on the order of 3 times 10 to the 13th such experiments every second. None of them anywhere has triggered vacuum decay. If the vacuum could be triggered by anything humans could build, it would already have been triggered long ago by the universe itself. The fact that we are here to ask the question is itself the strongest evidence that the answer locally is no. There is, however, a subtle wrinkle in this reasoning, pointed out by Max Tegmark and Nick Bostrom in a paper published in Nature in 2005. The wrinkle is this: any observation we make is, by definition, an observation made by an observer. If the universe were destroyed by vacuum decay, there would be no observers afterward to notice. So the observation that we are here, that the universe still exists, is automatically biased toward observations made before any decay event. This is called an observer selection effect. Tegmark and Bostrom's careful argument was that, even taking this bias into account, the natural risk of vacuum decay remains very small. They estimated less than 1 in a billion per year from all natural causes, including vacuum decay. But that the bias does, in principle, weaken the conclusion that nothing has happened anywhere in our past light cone. We see a universe that has not decayed because, in the worlds where it had decayed, there would be no us to see anything. This is a philosophical point as much as a physical one, and it does not change the bottom line. The rates are very low, but it adds a layer of subtlety to the way one thinks about cosmological catastrophes more generally. We are, in a sense, the survivors of a process that has not yet swept through us. The same line of thinking, sometimes called the anthropic principle in its various formulations, has been a topic of careful philosophical work for several decades. Tegmark and Bostrom's contribution, along with later work by Milan Surkovic and Anders Sandberg, was to apply the principle quantitatively to questions of existential risk. They asked, in effect, what we could and could not learn from our continued existence, given that our continued existence is a precondition for the asking. The answer, in the case of vacuum decay, is that the historical record gives us less information than it might otherwise seem to, but it gives us something. The age of the Earth, 4.5 billion years, and the age of the wider universe, 13.8 billion years, do constrain the natural rate of cosmological catastrophes. Even with the observer selection wrinkle factored in, the conclusion is that vacuum decay must, in fact, be very rare. The conclusion is not as airtight as a naive reading of the historical record would suggest, but it is not undermined either. The numbers, after every careful adjustment, remain reassuring. There is one more subtlety worth mentioning, because it has been the subject of careful work over the last decade. In some calculations, the presence of small black holes can act as catalysts for vacuum decay. A microscopic black hole of a particular small mass would, in certain models, dramatically lower the energy cost of nucleating a bubble of true vacuum nearby. The black hole would, in effect, act as a defect, a seed around which the new phase could form more easily. This was studied in detail in a paper by Ruth Gregory, Ian Moss, and Benjamin Withers in 2014, and has been refined by others since. The results suggest that, if very small black holes existed in the universe, they could catalyze vacuum decay at a much higher rate than the spontaneous tunneling rate. The fact that we do not observe vacuum decay therefore places limits on the abundance of such tiny black holes, or on the parameters of the Higgs potential, or on both. Most likely, it tells us that the relevant parameters are arranged in a way that keeps us safe. As of now, no evidence for catalytic decay has been observed, and primordial black holes of the relevant mass range are constrained by a variety of other observations. This is one of the more curious turns in the story. The same theoretical framework that suggests the vacuum may be metastable also tells us, by a process of elimination, that the parameters of nature must be arranged so that we are not, in fact, surrounded by catalysts. If small black holes of certain masses had been produced abundantly in the early universe, and if those black holes lingered long enough, then vacuum decay would have happened. We would not be here. The fact that we are here is, in this sense, telling us something quietly about the early universe. It is telling us that whatever catalysts might have existed were not abundant enough, or did not last long enough, or did not couple to the Higgs potential strongly enough to have triggered the transition. The universe has been, on the evidence, kind to us, or more precisely, has been arranged in such a way that the conditions for our existence have not been disrupted by any of the various processes that could, in principle, have disrupted them. Let all of these numbers settle slowly in the back of the mind. The point of them is not to memorize them, but to feel their general shape. The lifetime of our vacuum, if our vacuum is metastable, is unfathomably long. The rate at which nature has tested the vacuum, through cosmic ray collisions and other extreme events, is unfathomably high. And yet, here we are, in the long, calm interval between any such hypothetical events, in a universe that, by all the evidence we can gather, is entirely and reassuringly stable. The story of vacuum decay is not, in the end, the story of a sword hanging over our heads. It is the story of a depth of stillness so great that one has trouble believing it could ever end. In the last decade, something quietly remarkable has happened in laboratories scattered around the world. Physicists have begun to build small versions of the false vacuum on tabletops. Not, of course, the actual Higgs field. That is not something one can manipulate in a glass cell, no matter how clever one's apparatus, but analogs, mathematical cousins. Systems whose underlying equations look enough like the equations of false vacuum decay that the same mathematics applies to both. By watching what happens in the small system, one can learn something about what would happen in the large one. The first detailed proposal for this kind of experiment came from a collaboration that included, among others, Hiranya Paris and Silke Weinfurtner. The proposal was to use an ultra-cold cloud of atoms, a Bose-Einstein condensate, the strange phase of matter that emerges when a gas of bosons is cooled to within a millionth of a degree of absolute zero. In such a cloud, the atoms behave, in some respects, as if they were a single quantum object, and certain field-like excitations of the cloud can be made to obey equations that closely resemble the equations of a relativistic scalar field. By tuning the parameters of the cloud, one can place the system in a configuration analogous to a false vacuum. Then, one can watch, sometimes for milliseconds, sometimes for less, to see whether bubbles of the analog true vacuum form and grow. In 2024, a team based at the Pidivska Center for Bose-Einstein Condensation in Trento, working with theorists from Newcastle University and others, reported in Nature Physics the first experimental observation of false vacuum decay in this kind of system. They prepared a supercooled cloud of atoms in a state corresponding to an analog of a false vacuum. Then they watched. Bubbles of the analog true vacuum did, in fact, form, and they grew in a manner that matched the predictions of the theory developed for cosmological false vacuum decay. The temperature of the cloud was less than 1/1,000,000th of a degree above absolute zero, and the entire universe of the experiment was a region less than a millimeter across. Inside that small, cold region, the equations of cosmology played out in miniature. The setup, in its broad outline, was an exquisite piece of experimental physics. Two species of atoms, prepared in two different spin states, were combined into a single cloud at a temperature so low that the atoms behaved as a single coherent quantum entity. A radio frequency field was used to couple the two spin components, and by modulating that coupling in a careful way, the researchers could create an effective potential for the relative phase between the two components. By choosing the parameters of the modulation, they could shape that effective potential into a double-well form, a potential with two minima, one slightly higher than the other, separated by a barrier. The system was prepared in the higher minimum, the analog of a false vacuum, and then left alone. The temperature was tuned so that thermal fluctuations could occasionally provide enough energy to nucleate a bubble of the lower minimum, the analog of true vacuum. The researchers used absorption imaging, a standard technique in cold atom experiments, to capture snapshots of the cloud at various times after preparation. In those snapshots, bubbles appeared, small regions in which the relative phase had jumped to its lower energy value, and which then grew slowly by laboratory standards, expanding through the cloud until the entire system had transitioned. The whole process unfolded over a timescale of milliseconds, in a system spanning tens to hundreds of micrometers. A small, calm theater of cosmology, conducted at 1/1,000,000th of a degree above absolute zero. Other experiments of related kinds have followed. A group at Tsinghua University in Beijing, using an array of Rydberg atoms, atoms with their outer electrons excited to very high energy levels, making them sensitive probes of small effects, reported in Physical Review letters early in 2026 on a related demonstration. They engineered distinct quantum states with lasers and watched the slow, exponential decay of a metastable configuration as a symmetry-breaking field was varied. Their observations were consistent with quantum field theory predictions for false vacuum decay, and revealed, in some regions of parameter space, enhanced decay rates that had been theoretically anticipated but never directly seen. There have also been theoretical efforts using quantum simulators of various kinds, superconducting circuits, trapped ions, lattice gauge theory simulations on cold atom platforms, each of which provides a different angle of view on the same underlying mathematics. A consortium of researchers in the United Kingdom, led in part by Hiranya Paris at University College London and Silke Weinfertner at the University of Nottingham, has been pursuing a program called QSIMFP, Quantum Simulators for Fundamental Physics, dedicated specifically to building these analog cosmologies in the laboratory. The aim is not to terrify anyone, but to gather data, real, repeatable, statistical data, about a phenomenon that, if it actually happens at the cosmological level, can never be observed there. The laboratory, in this sense, is a window into a process whose cosmic version is, by its nature, hidden from view. These experiments are not, of course, simulations of cosmological vacuum decay in the literal sense. They cannot tell us whether our vacuum is metastable. They cannot tell us how long the Higgs vacuum will last. The substrates are different. The energy scales are different. The geometry is different. But what they can do is test the mathematical machinery by which we predict the behavior of false vacua in regimes where direct experiment is otherwise impossible. They are a way of checking that the equations themselves work, that bubbles really do nucleate in the way the theory predicts, that the rates depend on the parameters in the way the theory says they should. So far, the agreement between the analog experiments and the theoretical predictions has been encouraging. The mathematics, applied carefully, seems to describe the phenomenon as it actually unfolds. There is a kind of poetry in this, that to study one of the most consequential and apparently distant questions in physics, the eventual stability of the universe itself. The most useful approach has turned out to involve tables in basement laboratories, lasers cooling rubidium and potassium atoms, and the patient watching of a small cloud of gas under conditions colder than anywhere else in the known universe. The tools of inquiry have become, in this particular case, gentle. There is no need for monstrous accelerators, for impossible energies, for ambitious satellites. There is a need only for stillness, for the careful preparation of a small system, and for the willingness to watch what happens when the system is left alone in a configuration just slightly above its ground state. The universe, on its largest scale, may behave like a small, cold cloud. And by watching the small, cold cloud, we learn something about the universe. There is something deeply pleasing about this, a piece of theoretical physics, written down in the late 1970s in response to abstract questions about the structure of quantum field theory, has, 50 years later, been shown to describe real bubbles, forming in real cold gases, in real laboratories. The cosmological speculation has acquired an experimental shadow. We cannot watch the universe decay. We can watch a tiny system with the same underlying equations decay, and from that watching, we can refine our confidence in the broader picture. It is also worth noting that vacuum decay, or something very much like it, is thought to play a role in the very early universe, not as a catastrophe, but as a feature. In the original models of cosmic inflation, proposed by Alan Guth in 1981, the universe was thought to have been trapped, briefly, in a metastable state at very high energies, from which it tunneled, by something like the Coleman-de Lucia process, into a different state that allowed for the further evolution of the cosmos. Guth's original model had problems, which led to refinements by Andre Linde and others, in which the transition was thought to proceed by a smoother, slow-rolling motion of an inflationary field, rather than by abrupt bubble nucleation. But the basic idea that the universe has, in its past, undergone phase transitions in which fields shifted from one configuration to another, is well established. We are, in some sense, already living in a kind of bubble, a bubble of the vacuum that emerged from the early universe. The question is only whether, somewhere out there, somewhere in the future, or in regions of space we will never see, another bubble might one day nucleate within our own. Inflation itself, even in its smoother modern forms, is one of the most successful ideas in modern cosmology. It explains, with remarkable economy, several puzzles that had troubled the older Big Bang picture. It explains why the cosmic microwave background, observed in opposite directions of the sky, has the same temperature to within a few parts in 100,000, even though, in the older picture, those regions could never have been in causal contact with one another. It explains why the universe is so very nearly flat, why parallel lines, drawn across the cosmos, remain parallel rather than diverging or converging. It explains, by the imprint of quantum fluctuations stretched to cosmic scales, the small temperature variations in the microwave background that eventually grew into galaxies. By all of these tests, inflation works. The inflationary epoch happened, and in many of the surviving versions of the theory, the early universe was a place where fields lived in metastable configurations, where bubbles nucleated, and where the question of which vacuum a particular region of space ended up in was, at least partly, a matter of chance. There is, finally, a much grander speculation that is sometimes connected to vacuum decay. It is the idea of eternal inflation and the multiverse it implies. In eternal inflation models, the very early universe was filled with an inflated field, a hypothetical field whose energy drove the rapid expansion of inflation, that occupied a high false vacuum almost everywhere. From within this high false vacuum, bubbles of lower vacuum continually nucleated, each becoming a region in which inflation ended, and ordinary cosmic history began. Each bubble would be, in effect, its own pocket universe, with its own laws of physics determined by the particular vacuum at the bottom of the local potential. Most of these pocket universes would be lifeless. A few might happen to have parameters that allowed for the formation of stars, planets, and mines. We would, in this picture, be living in one such bubble. And the eternal background of inflating false vacuum would, theoretically, continue to nucleate new bubbles forever, in regions ever further from us, regions we will never see, regions whose physics may differ from ours in ways we cannot observe. This is a deeply speculative picture. It is not established physics in the way that the existence of the Higgs field is established physics. Many physicists are skeptical of eternal inflation as a literal description of reality. The idea grew out of careful work by Alexander Vilenkin in the early 1980s and by Andrei Linde shortly afterward, who both noticed that, in many inflationary models, once inflation begins, it tends to continue forever in some regions of space. The mathematics of this is reasonably solid within the theoretical framework. What is less solid is whether the framework itself describes reality. Eternal inflation depends on assumptions about the inflated field that we cannot directly test, and on the validity of the underlying physics in regimes, energies near the Planck scale, where our theories are known to be incomplete. It is a possibility, not a confirmed feature of nature. But it is a possibility connected, mathematically, to the same machinery that describes vacuum decay in our own universe. The bubble nucleation rate, the speed of the bubble walls, the geometry of the field potential. All of these are the same set of ideas, used in different cosmological contexts. To think about vacuum decay is, in some way, to think also about the possibility that our universe is one of many bubbles, all nested in a slow froth of inflating space, drifting apart from one another, never meeting, each going about its own quiet business in its own little hollow of the energy landscape. If one likes, one can imagine the entire cosmos on the largest possible scales as a vast, slow foam. Bubbles of various physics, of various ages, of various fates, most of them quiet, most of them stable, a few perhaps subject, eventually, to nucleation events of their own, bubbles within bubbles, hollows beneath hollows, in a tower of fields and potentials whose deepest floor, if it exists at all, no observer will ever see. This is a picture so vast that the human mind cannot really hold it. It can only let it pass through, the way one lets a long, slow tide rise and then fall, and accept that there is more here than anyone thought could contain in the so-called string landscape, a related idea that arose from string theory in the early 2000s. There are estimated to be something on the order of 10 to the 500th power possible vacuum states. Each of these would, in principle, correspond to a different choice of how the extra dimensions of string theory are folded up, and each would, in principle, give rise to different effective laws of physics in any large region settled into that state. Whether the string landscape is a true description of nature is, again, very much an open question and a contested one. But if it is, the picture of the universe broadens enormously. Our vacuum becomes one of an unimaginable multitude of possible vacua, most of which would not support life, a vanishing few of which might, scattered like rare flowers in an endless mathematical meadow. The probability of vacuum decay in this picture becomes the probability of slipping from our particular flower into a different and possibly less hospitable patch of the meadow. These ideas are not always comforting in their first formulation, but they tend, on reflection, to settle into a kind of equanimity. The universe is, in this picture, vast in possibility as well as in extent. The valley we live in is one valley among many. The fact that we live in a valley that supports life is, in some sense, the only fact about valleys that any observer of any kind could ever observe. We are here. The conditions that allow us to be here have held. And the calculated probabilities, both of our valley remaining stable and of any other valley supporting observers like us, are part of the larger conversation about why the universe is the way it is, and how it relates to the larger landscape of all the universes it might have been. What does any of this mean in the end for the small, particular world we inhabit? Almost nothing on any scale that touches a human life. The vacuum, if it is metastable, has lasted for 13.8 billion years and is expected to last for very, very many orders of magnitude longer than that before any local event might disturb it. The sun will burn out long before. The galaxies will drift apart long before. The last black holes will evaporate long before. By every reasonable accounting, vacuum decay is not a feature of our future. It is a feature of a future so distant that the word future loses much of its ordinary meaning when we apply it. And yet, the idea remains. It remains because it is woven into the fabric of how we understand the world. It remains because the same equations that gave us the Higgs boson, that explain the masses of particles, that predict the behavior of fields under quantum mechanics, also imply that there is a deeper valley somewhere in the energy landscape, hidden beyond a high mathematical hill, and that the world we know is a very long, very stable resting place, rather than the absolute floor. There is a kind of comfort in that. The world is older and more patient than us. It has settled into its valley over 13.8 billion years, and it shows no sign of leaving. If there is, in some unimaginably distant future, another configuration awaiting it, that configuration will be reached without any of us, and without any successors of any kind that we can recognize. The transition, if it ever comes, will be soft. There will be no observers in its path. The universe will have moved on, with no one left to be left behind. There is also a kind of wonder, the fact that we can ask the question at all, that we can sit in a particular pattern of fields and forces, having emerged from the long history of stars and galaxies and chemistry and life, and look back at the equations that govern us, and see in them a hint that they may not be the final equations. that there may be something deeper, something further down. We will never see it. Almost certainly, no thinking thing will ever see it. But the equations show us its possible existence, and we can hold that possibility in mind lightly, the way one holds a small, smooth stone in the palm, not anxious, not impressed, just aware. For now, the field is at rest. The Higgs sits at its value. The electrons go about their business. The atoms hold themselves together. The chemistry of the body continues, breath after breath. The stars burn steadily. The galaxies turn. The slow, patient music of physical law continues to play, unbroken, through every cubic centimeter of space, in every direction, as far as the universe extends. There is nothing that needs to be done about any of this. There is nothing to prepare for, nothing to guard against, nothing to lose sleep over. The very smallness of the numbers involved is its own kind of lullaby. If a bubble were ever to come, we would not know. There would be no warning. The wall, traveling at the speed of light, would arrive without any announcement. And inside the wall, the conditions for noticing would no longer exist. There is something almost merciful in that. The end, if there is an end of this particular kind, would be the gentlest end imaginable. Not a slow agony, not a frightening descent, just a quiet replacement. A new condition, instantaneous, in which the old condition cannot persist. No observer survives to mourn it. No observer survives even to know that anything has happened. The universe simply turns, in its small affected region, to a different page, and does not remember what was on the previous one. But this, again, is not what is going to happen. Almost certainly, by every measure we can apply, this is not what is going to happen for a very long time. The vacuum is calm. The numbers are vast. The stars will continue to burn for billions of years. The galaxies will continue to turn for hundreds of billions. The black holes will linger, slowly, for googles of years and more. And only at the very, very end, somewhere far beyond any cosmological epoch we have given a name, might the question of vacuum decay arise as more than an academic curiosity. So let the idea rest. Let it become, if it likes, a kind of background hum, a far-off thought at the edge of awareness, like distant rain at night, like a window left open in another room, allowing in a faint, cool air. The universe has its long calm and its long, deeper question beneath the calm, and both can coexist without disturbing each other. The hum continues. The hush continues. The fields rest at their values, where they have rested for 13.8 billion years, and where, by every estimate, they will rest for many, many more. There is something Sidney Coleman wrote near the end of his 1977 paper that has stayed with people who have read it. After working through the calculations, after deriving the rate of bubble nucleation, after discussing the implications, he allowed himself a single, dry sentence about the consequences of a bubble actually forming. He suggested that one's first reaction, on hearing of such a possibility, ought to be, as he put it, that this is dreadful news. But then, he wrote, on second thought, the dreadfulness fades. The numbers are very small. The probability is very low. There is, he concluded, no real cause for alarm. That is a good thought to settle into. The dreadfulness fades. The numbers are very small. The probability is very low. The hill between our valley and any deeper one is enormous. And the marble of the Higgs field sits where it has sat for the entire age of the universe, and shows no sign of doing anything else. It is an interesting feature of physics that questions which begin in apparent terror often resolve, on careful examination, into questions of geometry and patience. The fear that vacuum decay might happen tomorrow is, in the end, quietly dissolved by the calculations. The same equations that raise the question are the ones that answer it. The fields are stable on cosmic timescales by enormous margins. The only event that could plausibly disturb that stability, a quantum tunneling event of the right kind, anywhere in the volume of our observable universe, is, on average, expected to wait for a length of time so vast that no human notion of waiting could ever be applied to it. The patience required is not patience in any sense we have a name for. It is something else, a stillness so deep that it has no edges, no expectations, no countdown. The vacuum is full. The vacuum hums. The vacuum is, by all the evidence we can gather, stable on every timescale that touches anything we know. The picture of bubbles nucleating in deep space is a picture, drawn in the mathematics of quantum field theory, of something that is allowed in principle, and almost certainly forbidden in practice, for the lifetime of every star and every galaxy in every region of every observable cosmos. There is no need to hold the idea tightly. It can be loosened, allowed to drift, set down on whatever surface the mind has left for it. The story of vacuum decay is, in the end, a story about deep stability, about the fact that the laws of physics, having found their valley long ago, have stayed there with a steadiness so profound that even the most refined calculations of their possible departure return numbers too vast to mean anything. We can let those numbers be a comfort. We can let them be quiet at the back of the mind, like the ticking of a clock in another room. The universe in this picture is not on a knife's edge. It is in a deep hollow, well protected by the broad, slow shape of its own physics. Anything that could disturb it would have, by overwhelming odds, already done so in the 13.8 billion years that have already passed. The continued existence of stars, of galaxies, of the long, quiet patterns of cosmic structure that astronomers have mapped, is itself the evidence. The evidence has been accumulating for as long as anything has existed to accumulate evidence. The conclusion the evidence supports is gentle. We sit in a stable valley. We have been sitting in it for a very long time. We will sit in it, by every reasonable accounting, for very, very much longer. Far beyond all of this, beyond the energy curves, beyond the bubble walls, beyond the analog experiments and the philosophical asides, there is simply space and time and the slow continuation of matter and light. There is the Earth turning. There is the sun, 8 light minutes away, holding its long fusion patiently. There are the stars, drifting in their galactic patterns, as they have drifted for billions of years and will continue to drift for billions more. There is the cosmic microwave background, the faint afterglow of the early universe, filling all of space with a temperature just under 3 degrees above absolute zero, unchanged for the entire age of the cosmos. There are the laws holding everywhere the same. The Higgs at its value, the electrons in their orbits, the protons in their nuclei, the quiet hum of fields that has been the same hum, in essence, since the cosmos was less than a second old. If a bubble were ever to come, somewhere, sometime, far from anywhere we know, it would arrive in its own moment, on its own schedule, set by its own quiet equations. It would not be felt. It would not be seen. The wall would carry whatever it carried, and the regions it passed through would have, ever after, a different physics. We would not be there. No one would be there. The stars would be long gone by then, the galaxies dispersed, the black holes dissolved into long radiation. The bubble, if it came, would arrive at a universe already so empty and so cold that its arrival would be, in a meaningful sense, almost a punctuation rather than a destruction. A small change in the page, a passing from one quietness into another. And the stars continue, quietly, as they have for billions of years. There is nothing to do here. There is nowhere to be. The vacuum is the vacuum it has been, and the universe will still be turning in its long valley when you wake.